Hello, I'm Shoma Iwai. I will present our research titled Controlling Rate, Distortion, and Realism towards a single comprehensive neural image compression model. Image compression is essential for efficient storage and transmission of digital images. Recently, neural network-based image compression (NIC) methods have been studied, like this. The encoder and decoder are optimized using this rate distortion loss function. Here, R denotes rate term, which is the data size of the bit stream, and D is a reconstruction error, such as MSE. State-of-the-art NIC models have surpassed standard codecs like JPEG, HEVC, and VVC. There are two drawbacks of typical neural image compression. First, multiple models are needed to compress an image at various bit rates because each NIC model is optimized for one bit rate, like this. It leads to high model storage cost and high training cost. For the solution of this issue, some variable rate NIC models have been proposed, which we can control the bit rate with a single model. Second, NIC models trained with the rate distortion loss function often results in broad images like these images. To tackle this problem, some generative NIC models are proposed. These methods use generative models like GAN and diffusion model, improving perceptual quality like this. However, only few studies have addressed both of these problems within a single NIC model, and they come with some limitations such as narrow range of adjustable rates and performance gap compared to state-of-the-art single-rate methods. To overcome these limitations, we propose a novel variable rate GAN-based NIC method, and here are our contributions. First, we propose a GAN-based training tailored for variable rate NIC. Specifically, we explore discriminator designs and introduce a novel adversarial loss. Second, our NIC model can control not only rate but also distortion realism trade-off with a single model, achieving ultra-controllability. At the same time, the performance is comparable to state-of-the-art NIC models. This is an overview of our method. The NIC model takes three inputs: the original image, quality level Q, and realism weight beta. The model encodes and decodes the original image, and we obtain reconstruction. By using interpolation channel attention, ICA, and beta conditioning in the single model, we can control the rate and realism by adjusting Q and beta. However, our main focus is more on this light blue part, discriminator and adversarial training, and I will explain the details in the following slides. First, I introduce about our discriminator design. In variable rate NIC, the reconstruction quality varies based on the input quality level Q. Higher quality level Q results in high quality and large data size. We explored discriminator designs to effectively handle reconstructions of varying qualities. More specifically, our key question here is, should we use a single common discriminator for all quality levels, or should we employ distinct discriminators for each quality level? To examine this, we use two different types of convolutional layers in our patch discriminator. The first one is a convolutional layer applied for all quality levels, which captures features common across different quality levels. The second one is a convolutional layer for specific quality level, which run unique features at the individual quality levels. With these two layers, we design the following four discriminators, named as shared, independent, hybrid 1, and 2. The comparison of these four designs are shown here. Due to the time restriction, I explain only the insights we got from the comparison. First, discriminator designs influence FID, which measures realism, but have negligible effect on PSNL. Second, while convolutional layers applied to a specific quality level are crucial for improving FID, the convolutional layer applied to all quality levels do not show significant benefit. As a result, we use an independent discriminator here in our model. For more detailed discussion, please refer to our paper. Next, I explain our novel adversarial loss, higher rate relativistic GAN, HRR GAN. It is inspired by relativistic GAN, R GAN for short, but tailored for variable rate neural image compression. In R GAN, the objective is to maximize the relativistic reality score of the reconstruction compared to the original image, like this. So the NLC model is trained to generate more realistic image than the original one, and we found that this often leads to excessive penalty for NLC model, especially at low bitrate. Our HRR GAN, on the other hand, relaxes this issue. Here, the objective of HRR GAN is to maximize relativistic score compared to another compressed image with higher quality level. It relaxes loss function, mitigating the issue in R GAN. Moreover, by employing beta conditioning, a model to control the distortion-realism trade-off, our model can control rate, distortion, and realism within a single model, realizing ultra-controllability. As shown in here, we can control rate and realism with a single model. As a result, we can obtain reconstructions on different configurations, such as low bitrate and high realism, low rate and low distortion, and high rate and low distortion. In this way, our method supports diverse applications in various use cases. Now, we compare our model with existing NLC models. Since our model can control the balance between distortion and realism, we compare our model with state-of-the-art models in two modes, high realism and low distortion. In high realism mode, we use PSNR and FID as metrics and compare our model with generative NIC models. In low distortion mode, we use only PSNR and compare with distortion-oriented NIC models. First, we show the results of high realism mode. This graph shows PSNR and FID, and the x-axis represents BPP, bits per pixel, which is the dead size after compression. Since our model can control the bit rate, we obtain distinct data points with a single model, like this. Note that in a single rate NIC model, multiple models are needed to get multiple data points. First, compared with variable rate generative NIC model, Dirac 100, our method outperforms on both PSNR and FID. Next, compared with single-rate generative NIC models, our model achieves superior or competitive performance despite using a single model for different data points. Now we show the results in low distortion mode, so we compare our model with state-of-the-art distortion-oriented models. First, compared with other variable rate models, our method, shown in light blue, achieves competitive performance, especially at low bitrate, here. However, compared to state-of-the-art single-rate NIC models, such as ERIC with red dashed line, we observed a performance gap. Finally, we show a qualitative comparison between our model and state-of-the-art generative NIC models. In ours, we show 3 reconstructions under different configurations. As you can see, our low rate, low distortion mode achieves high PSNR with small data size, and the low rate, high realism mode looks more realistic than existing methods, and our high rate, low distortion mode accurately preserves the details of the original image. In conclusion, we propose a NIC model capable of controlling the rate, distortion, and realism with a single model. For variable rate GAN-based neural image compression, we explore discriminator designs and introduce HRR GAN, a novel adversarial loss. Our experiment shows that our model achieves competitive performance compared with SOTA NIC models in both low distortion and high realism settings. That's all. Thank you for listening.